E to E, that is end-to-end energy losses, energy related losses, energy influencing parameters losses that is happening in the industrial utilities from end to end. Let us monitor that and target the reduction of the same so that the input energy that is given to the plant can be optimized, can be reduced. Ultimately, it leads to the energy saving as well as sustainable health of the equipments in the industry. So, where are the end-to-end energy losses in the utilities? To start with, in the electrical distribution, from the powerhouse to the tail end, either the voltage drops or the PF either maintained at unity power factor at the powerhouse and almost around 0.5, 0.7 around at the PF, lagging PF at the load ends. From the motors to the driven machines, the torque drop or the speed drop, especially in the belt driven machines, and the RPM drops to optimize and reduce the gap, the demanded torque and the supplied torque, the gap to be reduced so as to have the energy savings in the motor related mechanisms, machines. Coming to the compressed air, the pressure drops at the compressor house and from the compressor house to the load end. Coming to the blowers and fans, either it may be a centrifugal blower or it's an axial flow fan, the Pascal pressure drops for the given flow rate of the blower or the fans and from the blower end to the tail end of the process. For the pumps, the pressure drop at the pump suction across the strainer and after the strainer what is given to the pump and what is the delivery pressure drop from the pump to the process, either it may be a tank or it is for heat transfer application, but what is it related, what is the pressure drop happening from end to end on the pressure drop across the pump as such. Boiler, the condensate return flow and the temperature drop to the feed water tank. Normally you find the condensate return water temperature is almost 90 plus, almost 100 plus, around 100 at the start of the equipment, at the return side of the equipment, rejection of the equipment, and this condensate return when it comes to the boiler it's around 70 or 80 or sometimes 60. What are all the drops that is happening and how this can be optimized? That is on the return line, but on the supply line, the steam supply line to any of the equipments from the boiler to the tail end, all the major heavy loads of the equipments. What is the steam pressure to be maintained, what is the temperature and what is the dryness of the steam, that is mattering more towards the thermal productivity of any given plant as such, especially if it is a packaged boiler. Coming to the cooling tower or the heat exchangers, normally all of us are monitoring the temperature drops, temperature difference across the cooling tower or the heat exchanger. That is more important, but that is more influenced by the pressure drops across the cooling tower or the pressure drops across the heat exchanger that decides the temperature drop across the given utility as such. So, the energy to the process interface, if you see from the EB, let us talk in terms of electricity, from the EB, the transmission and distribution losses occur more from the incoming energy port to the process demand, from the EB incoming side to the transformer, to the motor, to the bearings and couplings, to the pumps and to the control valves and to the piping network. You can see the percentage loss on each and every subsystems. That needs to be optimized, or are we running at an optimized loss of any given equipment, intermediate equipments. Only 30% is delivered to the heat exchanger ultimately, and so this big gap of end-to-end energy loss needs to be addressed to. What causes the end-to-end energy losses in the utilities? To accommodate the end-to-end energy losses, the input energy for the given utility, either it can be a compressor, it can be a pump, or it can be a blower, or at the electrical distribution also, it needs to be raised. Ultimately, this is an energy loss that is till now not noticed by the industry. Let us visualize the end-to-end energy losses that is happening and let us see how this can be optimized. Coming to the electrical distribution, the voltage drop end to end, normally it should be less than 10 volts and somewhere it happens to around 20 to 30 volts also. So the industry, what they conveniently do is they raise this temperature of the OLTC on the OLTC to 420 plus, so that almost around 390 to 400 volts reach to the tail end of all the motor ends. Coming to the compressor usage, the compressor is always at the tail end of the electrical distribution network, and since the compressor, especially the screw compressors, are running at a service factor of 1.2, it needs always 420 volts at its incoming. But when all the other equipments throughout the plant can be run at 390 to 400 volts, the compressor wants only 420 volts, so that the energy loss in the compressor, because the fully loaded compressor, the efficiency is better when it is only at full 415 volt plus. Some of the machines or the lines, pneumatic lines, the fitting links are there. The compressor header pressure needs to be raised from 6 bar to 7 bar or even 8 bar also, when the machine rated demand pressure is only around 5.5 bar. The pressure drops coming in the compressor, existing in the compressor house, from the compressor house to the main header to the sub header, all from say what is needed at the load ends, pneumatic load ends. Based on that, the header pressure has to be raised to accommodate the end-to-end pressure drops as such. Somehow the process has to be run by accommodating the losses, pressure drops. Many of the machines want to coming to the blowers and fans, many of the machines want only 600 pascals, let us say for an example, as rated, but the leaks inside the machines, individual machines, or the leaks in the header pressure, especially in the flanges, the industry needs to keep it around 1000 pascal to run the machine at 600 pascal. Almost 30% kilowatt is lost in between because of the end-to-end energy losses, especially in blowers and fans, for the pascal to be optimized for the given equipment. The pumps that are running at say 3 bar to transfer the water to the tank, but scaling inside the lines and the leakage in the gland and other things, what happened is the pump needs to be run at 4 bar only, then only the rated flow to the tank is achieved. These are all the happenings that is happening in the industry. Each industry segment has their own norms, and are you within the E2E norms, best operated practices in your industry, in your segment. Coming to the motors, especially the electrical input to the motors, you can see the load and compensation is mandatorily required for all the 3-phase motors above 5 HP. You can see from 5 HP to 100 HP, at around 50 to 75% is your motor loading average in general. If you find almost it's around 0.7 to 0.8 only, around 0.5 to 0.7 or 0.7 to 0.8 only. So definitely this needs to be improved to 0.8, lagging power factor of 0.8 plus, that is more than 0.80 to be kept at the motor end. Then only the line losses or the voltage that is dropped from the incoming to the motor also can be improved upon. So, and the motor also works better. Now the efficiency, ultimately the motor as an system efficiency improves as such. Coming to the electrical distribution network, the motor loads are having a poor power factor only. High voltage drops are seen in the industry. Some industries even report almost 30 volts plus as a voltage drop. So this maintaining a unity power factor at EB and it's not correct. You have to increase the power factor, lagging power factor from 0.8 at the load ends, gradually raise it to the SSB at around 0.9, and from SSB to the EB incoming side around 0.2, 0.97 as the strictly, if you maintain a slightly lagging power factor at the EB incoming side using a 3CT APFC, automatic power factor control at the powerhouse, definitely you see to it that the safe volts is given to your plant. At the same time, harmonics is also the reduced harmonics, current harmonics is already seen as such, observed during our audits. So the KVA improvement, if you see any of this 50 HP motor, after doing the capacitor compensation, load and capacitor compensation, you can see the almost 3% the decrease in the power at the motor end, and you can see the KVA drop is almost 17%. The demand from the motor is dropped by 17%. The power factor also improved from 0.8 to 0.92. So this is how we have to stabilize the power factor from the motor end to the reduce the gap. The gap is wide. Let us reduce the gap. Coming to the blowers and fans, it is all variable torque loads. If you see the graph, you can see on the y-axis on the torque and the x-axis on the speed. If you see the constant torque machines, all the production machines are all constant torque machines more in general. And all the variable torque loads like blowers or centrifugal operated pumps or even these fans, axial flow fans, every of these utility follow the affinity laws, and they have a excellent scope for energy saving if the RPM to the machine is optimized and the energy influencing parameters like the Pascal, static Pascal, and the flow from the machine or to the machine, either it's a suction or delivery blower, if that is optimized, definitely it can see the excellent energy saving here. But mandatorily the VFD becomes a mandatory retrofit for all your blower systems in the plant as such. There is if you see the graph here, the x-axis, the variable torque loads, especially in the variable torque loads, there is a clear gap between the supply and the demanded torque. You can see the curves. What is the torque curve on the top and the HP curve is the kilowatt curve on the power curve on the bottom. The gap is very much visible at the partly loaded, around 50 to 60% loaded for a given blower, and this is what is emphasized here. And if we are able to reduce the gap between the torque and the speed of the given blower, this is facilitated by using the retrofitting the VFD to the given blower. Ultimately, thousands of case studies has been done in blowers and fans by using this cogged belt conversion and this pulley conversion, resizing the pulley, redesigning the pulleys so that the VFD retrofit facilitates the energy savings. At the same time, it is able to maintain the blower RPM. At the same time, almost 15 to 20% of energy savings is possible. That is instantly happening in thousands of case studies which we have recently observed for the past 3 or 4 years now as such. The energy losses in the intermediate stages of power transmission, especially on the belt operated machines, either in the production or in the utility machines, when the replacing the belt is routine, but the worn out pulley is not taken care. It has a life of only around 40,000 hours. Say continuous running means around 5 years. After that, the pulley also needs to be replaced because of its worn out, and the wear and tear in the pulley definitely mandates to be replaced. This pulley needs to be replaced, and if the same is replaced with instead of a V belt, classic V belts, cogged belts are used, where with matching pulleys, the RPM also loss is also, the slippage in RPM also is addressed to, it is kept less around 1 to 1.5% only, and the power transmission loss, that is very much addressed. Intermediate power transmission loss is very much addressed, and the productivity can be increased. It's increased in many of the production machines, in many of the industry segments. They report after this implementation, they say their productivity also has gone up by 10 to 20% as well at a reduced power consumption. So thermal imaging is a must, especially when you are assessing or diagnosing the intermediate power loss that is happening in all your utilities. This we have done during our energy audit in 2012. You can see the belts and pulleys almost boiling condition, almost 90 degrees or 100 degrees. This is really happening in the industries, present day industries. Definitely it can be taken care, and see to it that always the motors and the belts or pulleys, whatever it may be, it is only warm around 50 to 60 degrees. More than 70 or 80 only, the hotter motor is a symptom of inefficiency for a motor related system as such. So the compressor, coming to the compressor, I am just talking about different utilities, what are all the end-to-end energy losses happening inside the utility and from the utility to the plant. So the E to E energy losses, basically compressor is like it's a dynamic process variable in any of the plant where you are concerning. It's very fast and it's very dynamic. The pressure drops due to usage and leakage and more of cleaning. See, three applications happen, especially in the compressed air: for power air, for instrument air, for leakage in the lines and in the systems, in the equipments, pneumatic equipments, and during the cleaning application. Normally what is freely delivered at the compressor inlet, but it is stopped due to the air intake filter, due to the choke in the air intake filter. The compressed air treatment gains more of prominence now in all the industries now, at the receiver, at the filters, at the refrigeration dryer, and ultimately the compressor house needs to deliver a cool dry air to the plant as such. The compressor to the compressor header piping orientation, if the compressor flange is around say 2 inches, the header needs to be only at 3 inches. Also the piping and the flow for given flow, what is the piping to be laid, that is also it is already told by all the compressor OEMs and by the Bureau of Energy Efficiency manuals also, energy efficiency manuals. So you need prompting switches, prompting devices like differential pressure or a delta Pascal pressure switches at the air intake, across the dryers, refrigeration dryer, across the filters. These are all mandatory. Instead of seeing this yellow and red bulb as a band indicator, let us have the definite value of the Pascal drop happening at all the filters and dryers as such. The pressure switch low at the heavy pneumatic load end, at the tail end, or at the heavy pneumatic, that shows there is a heavy pressure drop at the full flow of the compressed air. So this is to be optimized. So all the pneumatic loads in any of the plant, it needs an air bottle or a mini air receiver at the air intake to give a steady non-pulsating compressed air to the system. This makes the system also healthy. This makes the pneumatic components, that is subsystems of the system of the existing equipment also healthy. The leakage can be corrected because all the PPR piping, fittings and all, it has its own definite lifetime, and if it is replaced with either brass or SS fittings in all the pneumatic impulse lines or the actuation lines, tubings, definitely the leakage you can definitely bring it down to the minimum most possible, less than 5% or less than 2% also. So the cleaning air, next comes the cleaning air, where the cleaning air application definitely needs a buffer receiver and scheduled cleaning to be taken by the plant. That is what the maintenance, when you are planning for your maintenance, this cleaning also, it needs to be scheduled. Also the buffer air receiver sees to it that the pressure drop does not happen to the compressor, and the compressor is not put to extra strain because of just opening many hoses cleaning at the same time as such. Coming to the compressor FED, free air delivery now, this is a case study. In fact, this case study is seen in each and every of your compressor. Air intake filter at 100 Pascal, the compressor gives, say 110 kilowatt compressor gives almost 720 CFM, the rated flow. If the same air intake filter got choked within 2 months, instead of the stipulated 3 months and above, it got choked within 2 months, let us say, at 2700 Pascals, the flow dropped to 13%. This is what we have to keep it in mind, and let us monitor the air intake delta P static Pascal in either digital or using an analog gauge, and routinely monitor that and clean that, says that you get a rated delivery of airflow, compressed airflow. Also the end-to-end compressed air pressure drops happen due to many of the solenoid valves, bleed type solenoid valves, or the timer type drain valves. Especially in the compressor house, the timer type drain valves, they are heavily draining the air, as well as the bleed type puppet type solenoid valves, where they are all used with neoprene, lubricated neoprene O-rings are used in all the puppet type solenoid valves, that needs to be regularly taken up for servicing, overhauling and replacement, especially the O-rings, so that any of the bleed type solenoid valves, if they are bleeding very cyclically, that also leads to the flow pattern of zigzag flow pattern. Ultimately you can see a 45 kilowatt machine, it is delivering around 220 CFM, but it is taking almost 48 kilowatt here. This is what each and every flow, the compressor above 50 HP definitely needs a in situ flow meter, single, that is a insertion type flow meter to be fixed at the point at the compressed air header after the refrigeration dryer in the compressor house as such. Energy loss happens in the intermediate stage of the compressed air distribution also. The compressed air flow is less and the discharge temperature is high, means above 5 degrees above the ambient means. Ultimately the flow gets less, and the compressor needs to pump in more, it needs to deliver more, and the kilowatt consumption automatically goes up. The dryer needs to be double the size of the capacity of the compressor size, so that the pressure drop across the dryer, when there is a full flow in the compressed air header, the pressure drop definitely matters more. Normally it is said around 0.2 kg or 0.15 to 0.2 kg, but in some industries report almost 0.5 to 1 kg also the pressure drop happens, because the dryer becomes derated or undersized for the given compressor rated capacity as such. Compressed air leakage, this direct and indirect results of the leakage, definitely it is telling upon the compressed air health. If you see the compressed air leakage, it can be reduced as per the industry segment norms. Each and industry segment has their own norms, and based on that, let the leakage be reduced. Let it be 2% or let it be 5% or let it be 10%, and let us see to it that leakage is kept to the minimum as such. Many industries are running their compressor almost 2 to 3 bar also, 1 to 2 bar or 2 to 3 bar at higher header pressure, just to accommodate the leakages that is happening intermittently. Also, in some industries they are even running a third compressor just to address the leakage only. So it is time to change the header piping to aluminum or SS piping, depending on your definitely it is an energy saving, but it is to be well thought about and needs to be taken. But at least in the compressor house, let us try to avoid all the sharp L and T bends and make it long and conjoining bends, 45 degrees conjoining bends. So plan to replace all the PPR fittings with brass and SS fittings to avoid the leaks, and leaks will be brought to the minimum most possible. Coming to the blowers, the blower, if you see the observe or view the blower as a system, the subsystems, either the motor or the bells and pulleys or the impeller, the ultimately the efficiency of the blower is around 40 to 50% only in the present day industry, or even in the building segment also. How this can be addressed to as such? The compressor pressure drops are visible to the industry, and which industry takes immediate action, whereas the blower Pascal pressure drops are not visible. You can have a digital Pascal gauge which costs less than 10,000 rupees, and definitely it can be detected by intermediate monitoring in intermediate stages. Case study is that a blower rated 2200 Pascal for the given flow rate, each machine wants only 600 Pascal. But this blower is oversized, and 600 Pascal demand and 2200 Pascal supply is totally not logical as such. This is oversized by the process and the equipment OEM. This needs to be optimized. And the prompter is the delta Pascal switch across the filters at the machine end needs to be optimized. Let us try to optimize the minimum Pascal, static Pascal at the machine, and the static Pascal drop from end to end across the filters also. Let us try to bring it to the optimum. Let us ask the OEM, filter OEM, what is the maximum allowable pressure drop, static Pascal drop available when the filter is in full flow, when the filter is in minimum flow across the filter, what will be the pressure drop? These are all the inputs to be taken by the maintenance people. Accordingly, we can plan it as such. The Pascal drops also demand, as per the affinity laws, the Pascal drops demand heavy blower power, and ultimately the blower power goes up by 20 to 30% also, because of the pressure drops, intermediate pressure drops across the from end to end as such. So you have to tackle this by way of blower fan design, going for aerodynamic profile, then the orientation of the blower towards the process, and the tip clearance. That's what I want to come to you next as such. See, the blowers are axial flow fans. Let us see the axial flow fans. The tip clearance is a neglected area where the energy loss is appreciable, more than 10 to 50% also the flow drop is there, and even the static pressure and the airflow also drops by 10 to 15%. Normally the norms is 1% of the blade length. Let us say it's a 1200 mm axial flow fan. You can see almost 50 mm is the gap between the impeller and the casing. Normally it is supposed to be, let us say it's around 500 mm is the hub, around 700 mm is the total blade length, around 350 is the individual blade length. So it should be less than 1%, around 4 mm is the allowable tip clearance normally maintained by any of the best managed, best operated industry. So once the tip clearance goes more than 1%, definitely the flow and the static pressure losses more, and it's only short circuiting as such. You can see the blower on the left side, you can see the blower on the right side. Both the blowers are inefficient because the aerodynamic profile is lost here. It is not here in this, so that needs to be improved upon as such in the existing fans as such. Coming to the, see, I have just covered the compressor, blower, pumps and all the other electrical distribution including the motors. Coming to the boiler and steam, see, ensure that the steam is separated from moisture at end to end. Normally, the package, this input we need more towards the package boilers. When the boiler is packaged and given to the end user, definitely the moisture content from the boiler to the end user, the moisture is very much more, and this boiler always delivers only wet steam only. So, to improve your thermal productivity in your industry, end-to-end boiler to tail end or the heavy load end, even in the PRDS or a flow meter installation, the moisture separator is very much required. It needs to be installed at the upstream of the PRDS or the flow meter installation apart from the boiler. See, these are on at the flow meter and PRDS installations, and for the boiler at the boiler delivery out and any of the heavy equipment at the input, the moisture separator needs to function. Thanks to the PCRA, Petroleum Conservation Research Association, it's an integrated service provider that has been working under the Ministry of Oil and Gas, but they have given thousands and thousands of case studies, and it's a decade-old case study. It's an excellent case study on fuel savings based on their fuel oil diagnostic studies done on thousands of industries across India. And this case study on a package boiler around 850 kg, almost it's around 1 ton boiler, while they are using LDO as the fuel, and 50 liters per hour is the normal consumption. Without this boiler is on the left side you can see it's a boiler without moisture separator. The boiler runs for 18 hours a day, and it is given for indirect heating for any of the process requirements. You can see the thermodynamic or thermostatic drops or the float drops, everything is traps or everything are maintained at the equipment side, at the delivery side, return line of the equipments, everything is maintained. But at the input of the equipment, moisture separator is not there. The moisture separator is installed between the boiler and the equipment now. At two ends, at both the ends, you can see the fuel dropped to 45 LPH, almost 10% savings in fuel, and the boiler running hours dropped from 18 hours to 14 hours. Ultimately, the energy saving was almost around a macro view of this retrofit of moisture separator at the boiler end and at the tail end, especially on the heavy load end. This gave an overall fuel savings of 10%, around 30%, per hour fuel rate reduced by 10%, and the running hours reduced by 22%. And investment is just 50,000 only, and the annual reduction in the fuel bill is more than 10 lakhs. Say, this is a mandatory moisture separator retrofit to be done in each and every package boiler. Only the end users have not taken the priority to install the retrofit the moisture separator at the boiler steam flow output as well as at the any of the heavy or tail end equipment at the, see, when the boiler to the equipment distance is more than say 50 meters or 100 meters, definitely the moisture separator needs to be there at the intermediate stages also, especially at the main header to the branch header where it is branching out. At those places, whatever the moisture that is collected in the steam header, that needs to be removed so that the conductive dryness of the steam can be very much improved. The dryness of steam at the load ends improve the thermal conductivity and the less run hours also for the given thermal steam operated process. Steam traps, normally it used to trap the steam at the returning line of the equipments, and only the condensate is returned back to the boiler. But what you have done towards the incoming of the wet steam when it is entering your equipment, have you installed the moisture separator in all your equipment? This is mandatory. It is not that I am trying to promote a moisture separator, but moisture separator is steam is a two-phase liquid or a fluid that is going in the process. It is supposed to be 95% dry and only 5% dry. The wetness is allowed in the normal best operated practices. What is there in your system, in your industry? So, the moisture separator needs to be installed in all the PRV. See, in some industry, we have come across during the energy audits, we come across some industries, they are buying from the steam supply ESCO OEMs, they have installed this flow meter installation, but the moisture separator is not there before the flow meter installation. Ultimately, the flow meter is recording higher. They are paying almost 1 kg for around rupees 150 or 1.50 or 1.2 or 2 rupees per kg of steam. But the kg of flow of steam is monitored, is recorded more because the moisture separator is not there at the incoming of the flow meter installations. So, moisture separator is not there, let us say. Definitely it causes wet steam, it causes less of thermal productivity. Also, the pipelines also get corroded. So, for sustainable thermal health of the equipments and the productivity, moisture separator is needed end to end as such. Coming to see thermal imager, definitely every thermal imaging we are using in the industry, everyone is just dedicating that only to the powerhouse or limiting to the powerhouse application, electrical application. But thermal imager finds an excellent scope in all seeing the temperature gradient in throughout the process in any main or branch header or any of the equipment related industry where the temperature is above the ambient, and this can be monitored, and you can definitely assess the temperature gradient, what is optimal, what is normal, what is abnormal, and what are all the deviations are there, how this can be addressed to. So, see, this is a boiler case study which we have done during our audit. We found almost the boiler feed tank is receiving almost 90 degrees centigrade, but the insulation is not there from the boiler to the pump to the up to the boiler end as such. From the feed tank to the boiler end, insulation is not there. Ultimately, the temperature at the boiler end, if you are able to see in the thermal imagery, it's only 55 degrees. So, heavy drop of temperature is happening because the pipes are left bare. Wherever you are using the steam system, you need to have the insulation end to end on all the piping, not only on the piping, it needs to be there on the flanges, it needs to be there on the fittings. If not possible to do aluminum cladded, glass wool and aluminum cladded insulation, you can even use an asbestos roof in any of your steam related pipings and fittings, and definitely you see here that the heat is always house arrested within the piping, not to escape it out to the atmosphere. It is a huge loss to the industry that is silently happening to your industry. Coming to the pumps, the piping losses are killing more in the energy efficiency in the pumping system. And what can be done in the short term or in the long term? One critical input here in the pump flow system is at the suction of the pump or the delivery of the pump, the velocity at the suction, the immediate suction or at the immediate delivery needs to be lower at the entry and the exit of the pump. So, to fix today the eccentric expander fittings, eccentric type expander fittings in such a way that the flow is reduced and made optimized at the input at the exit of the pump. You can see the 20% decrease in diameter, say friction increases by 3 times. Instead of a 4-inch pipe on the header, if you are having a header as a 4-inch pipe, the pump flange is around 3 inches. If you say the header needs to be 4 inches, it needs to be one step ahead of the pump flange size. So, instead of a 4-inch pipe head flange, the header they have installed around 3 inch only, almost 80 mm only. The friction losses will be very much more, almost 70% friction losses happen in the short bends and L bends also. You can see the rigid PVC piping coming to the water lines, especially the cooling water lines or any of the lines that are used for the heat transfer applications. The rigid PVC pipes, CPVC piping from GI piping or this MSERW piping, it gives an energy savings of up to around 20% sustainably. This is more important. This changing the MOC of the piping material, definitely it improves the energy, it gives a sustainable energy savings up to 20%. And the farmer has already changed for all these GI and MS pipes to all these rigid PVC pipes. The industry needs to change this in all their water lines, and all the compressed air piping also going for a aluminum or a SS piping depending on the industry type and demand. This gives a foolproof energy savings and sustainable energy savings for another decade or two as such. Almost 20 years they give the guarantee for the aluminum or the SS pipings and fittings as such. Brass fittings and SS fittings here to say. Piping improvements. as I said, conjoining pipings. See, leave alone the pipe sizes, the piping improvements call for conjoining pipe sizes at 45 degrees bend, and each and every pump needs to be conjoined to the main header in such a way that the turbulence does not happen at each and every T junction, and the conjoining flow sees to it that the pump or the water flow towards the water flow at the header. Ultimately, this also makes the flow laminar and not turbulent. Ultimately, the system efficiency improves sustainably thanks to the Texmo installation where you have done the energy audits. See, these are all the case studies, these are all the fine pointers which we have observed and given the recommendations in all the industries, and these all have been discussed well in all these 5 books on this general industry, compressed air, on all the belts and pulley drives, and on the textile mills, and on the building segments, which has enormous case studies. So you can go through it and definitely give your inputs after doing the implementation as such. So ultimately, the bottom line is prompting the devices at the equipments. We call it as a EOL, end of line resistors we use in the safety side, especially on the safety network of the electrical safety. It is a end of line. What is the prompting devices to be kept as local and remote alarms? The prompting devices can be local indicator or a local blind switch with the alarm to local or remote, audible alarm or visible alarm, local or remote also. To avoid the nuisance alarms at the especially on the tail end of the heavy load end, you can link a time delay timer across the pressure switch low, let us say, so that few seconds, if the pressure switch is pressure is definitely low for more than sustaining for few seconds, lower for few seconds, then this can definitely give an alarm, and let this not be a nuisance alarm, or it is only giving an alarm. It need not be linked to tripping, and if it is critical, it needs to be linked to tripping also. So if the parameter is critical, you can definitely plan for IoT or analog transducers or digital transducers or digital transmitters, and along with 485 232 interface, you can definitely tag it to your plant computers also. All the tail end, see, end to end energy related influencing parameters also needs to be monitored. That is what the contention of this session is. So it can be on volts, it can be on the power factor, it can be on the line pressure on the compressed air, or in the blower, or in the fan, or in the pumps, and the temperature gradient end to end. That is also more important. The electronic motor relays play a vital role now, and it is just costing almost near to the thermal overload relays only, but especially they are used for dry run preventer application, especially in the submersible pumps. This electronic overload relay takes care of single phasing, current sensing preventer, and once it is set for the dry run, say around 80% or 70%, once the equipment goes for idling or dry run, this also shows the equipment is idling. This gives an indication to the total productive equipment of the system as such, total productive monitoring and maintenance of the system. So condition based monitoring of equipment is not enough now, but the ETE is more important. The time and transmission distribution losses also happening silently in your industry. It is time to address it, focus it now and address it now. Thank you, thank you, thank you.